figure that out here. We are, oops.
I tried to get it to a swim before for my camps, and I didn't have any time during last year's.
Oh, come on, what's going on with this thing? Whenever I leave class, I always end up leaving class with my computer on while it's uploading videos, so it ends up staying on too long, and then it freezes everything, and then we have to start over again. I need to turn this thing off at some point. Let it rest. Sorry, last week we finished up chapter 5, and we set up the first exam. Excuse me. So we're through with chapter 5, and the first exam is posted. That's where we're at. Let's log in and take a look at that quick.
So how does the exams work?
So the exams are taken through My Open Math, but you do have to take them with a proctor. You'll be required to enter in a password, and your proctor would have that password. So you can take it in the assessment, take it in the Student Success Center, which is down by the bookstore, between the bookstore and the library down there, in the other building. And they are open Monday through Friday, normal business hours kind of times. So you can take that, it's due tomorrow, it says. But if you need to take it another day, just tell me, we'll figure it out. It's a 2.5 hour time on the exam. It is timed. And you will be allowed your calculator and you can use your textbook on the computer. And you can, let's see, what else can you do? Notes are not allowed on the exams unless they are taken within the textbook. So if you are using a printed textbook or an online textbook in PDF form and taking notes from the textbook, then that's fine. But I do want you to use. I want the textbook only for.
Do they have computers in that?
They do have computers there. You can also use your own computer there if you want to. So. If you use their computers, they won't have any problem. If you want to use your own computer, they will almost certainly call me to make sure that's okay, because they always want to check that. But they do have computers there that work just fine with My Open Math. Been using them for years now. Scratch paper and pencil you can use as well. So the best way to use your computer, to use your online textbook with the test, is to just open 2 separate tabs and just go back and forth. If you try to go to it during the test, it will actually lock you out of the test if you leave the test page. So just open the book up first and then open the exam and just go back and forth and spit it out. Yes, sir.
Are we able to do this at home or?
No, I have to take it with the proctor. So you have to take it here at the Success Center, or you can also take it at the public library. They'll proctor for you as well. They'll just charge you. So, you can do it at any other school you want to, but they'll also charge you. So taking it here is your cheapest option. And just email me if you need to take it some other time this week. We can try to get that done as soon as possible.
I didn't get the homework done. I tried to go back a little bit this morning.
For chapter 5? Or chapter?
I don't think I got it.
Okay. Just email me and tell me, and I can extend those for you. Just tell me when you want them extended to, and I'll extend them for you when you're finished up. But that's where we're at. This week it's just going to be 3 of us. Packer's gone to scout camp. Andrews at the speech tournament thing. And Cassie's supposed to be connected with us today. Excuse me. She's not connected yet, but yes, sir.
So weird question, but do you have a bottle?
Do I have a bottle opener? Yeah.
Because I thought this was a twist off, but it's not.
I am an Eagle Scout, so I am prepared.
Thank you.
There you go. My dad gave me this little mini leather manual, and it has proved extremely useful. There's Cassidy. How you doing?
Hi.
Hello.
Sorry, I'd fallen asleep and I didn't wake up to my alarm.
I fell asleep earlier, about an hour ago. I had to get up and go buy a milkshake so I could have some energy this afternoon. I spent almost all morning outside in the fields at the research farm, so I was kind of tired. I understand.
Research fields. What?
I'm sorry?
The research field?
Yeah, UNL has a research farm across the street here from the college, and I do some work out there with the professors and research groups out there. So we were working out there today. So that's where I was this morning. Yeah, kind of tired. Yeah. Okay, so today we're going to start chapter 6. And as I mentioned earlier, we're going to try to start moving a little quicker through the chapters now. We're going to be doing rotational motion. Let's take a look at the calendar. Today is the 19th, and the class ends on the. When does the class end? Why can't I move my calendar? I don't know. But anyway, today is the 19th. We have 2 more weeks this month, and then we have, of course, 4 weeks and a little bit in July, and then just a couple of weeks in August before the class is over. So it's about, let's see, what's that, about 8 weeks. We have about 8 weeks left, and we have about 10 chapters to go. So we need to double up on a couple of weeks with chapters to try to finish up everything. We have 10 or 11 chapters to go. I don't remember exactly.
I have in my calendar that last day is the 11th of August, which is Friday.
Yeah, so it ends the second week of August there. 1.5 weeks in August. That's correct. And we're supposed to cover everything through chapter 16, actually chapter 17. So we actually have 12 chapters left. So we have about 7 or 8 weeks, and we have about 17 chapters. So we're going to be doubling up on chapters. Most likely we'll double up. I don't think we'll get into doubling up this week quite yet. Let's see, where are we? Right here, rather. 6 and 7. We probably, I don't know, if we might be able to double up this week. We might not. But next week we might double a little bit, add a little bit of chapter 8 to chapter 7. And then when we get here to chapters 11 and 12, we will probably double up both those into 1 week. And we might do these gas laws and heat transfer methods into 1 week. And probably oscillatory motion and hearing into 1 week. So we'll be trying to do that here soon. So just be prepared for that coming up. It will be happening. But today we're going to start moving out of the straight line motion world into a little closer into the real world now. Which means we're going to start turning. Right? We have our race car on the racetrack, Grand Prix. we're going to be studying a lot of what we call uniform circular motion, which means that we're going to be studying objects that are moving in circles at a constant speed. And the circle will have a constant radius. So we'll have a constant speed around a constant radius circle. Pretty simple circular motion, but it has a lot of important implications in the real world for us. The first thing that we're going to have to do is we're going to have to actually change coordinate systems. When you're talking about rotation, using the XY coordinate system is extremely painful because everything that you do is going to involve a sine or a cosine or a tangent or both or all three or whatever. So it just becomes really painful to use that all the time. So what we do is we convert into a new system that doesn't use X and Y, one going horizontally and one going vertically. We actually convert into what we call radial coordinates, or sometimes called cylindrical coordinates. But what it really is that our two coordinates are, rather than being two distances in directions that are 90 degrees to each other, one of them is an angle and one of them is a distance. And that is what we call our radial coordinate system, or our cylindrical coordinate system. So let's talk about it here. Here is a disk, just your regular CD that most people don't use anymore anyway. But if you consider a line, you draw a line along this disk right here, and then you rotate that disk through some angle around the center of the disk. We can call that delta theta, and we've dealt with angles before, so that's not a big deal. But we do put the delta in front because we start at one particular place in angle, and we end at a different, this line that we drew ends up at a different particular place in angle. And so we define a beginning angle and an ending angle, and then we take a difference between those angles, and we call that angle delta theta. And it turns out that you can actually do some relations. There are some relations we can work out. If you want to calculate the path along the edge of that disk, that path we're going to call delta S. So it's a curved path, and we want to know how long that curved path is. Delta S is actually, there's a relationship between the angle delta theta and the distance delta S, and the relationship is R. And this is something that you all know, even though you may not recognize it yet. Does anybody recognize what this formula is? What if this angle goes all the way around the circle and it becomes 2 pi? What does the delta S become? What do we call it when we go the distance around, the entire distance around a circle? What do we call it? The circumference, right? And then this equation becomes circumference over r equals 2 pi, or circumference equals 2 pi r, right? So this is actually the formula for the circumference of a circle. But it's not for the entire circumference of a circle, it's just for some little piece of it, which we call an arc. This is an arc or an arc length. And for this little piece of the arc of the circle, and this little piece of that angle that is associated with that arc, you can use the same equation that you use for the circumference of a circle. And here it is again written, 2 pi equals delta theta, yeah, that's right, 2 pi equals delta theta. And that's for a complete rotation. If you go all the way around the complete rotation, you get 2 pi times r, which is the circumference. And if you divide that delta S by r, you get just 2 pi, and that ends up being equal to delta theta, which is just an angle. So what we've done in this equation right here is we've shown that the total amount of angle around a circle, when you consider this equation for circumference, the total amount of angle when you go all the way around is equal to 2 times pi. Well, is 2 times pi a measure of angle? Sure, if we want it to be. And so we give it a name. We call this measurement of angle, we call it a radian. And there's 2 pi radians for every one full revolution of a circle. So if you go around an angle in any particular plane, and you go all the way around to the angle that you started with, if you start here at this angle right at this blue line, and you go all the way around and end up at that same angle, end up at that same place in angle, then you've gone through 360 degrees, or you've gone through 2 pi radians. Okay? Now, why do we use 2 pi radians? Because it makes more sense, right? We defer to the 360 degrees thing because that's what has been used throughout time, but there's no reason that we should use 360 degrees. It's a random number somebody chose. It's just doesn't have any scientific basis into it. However, the number 2 pi has an extreme amount of scientific basis to it because it is the relationship constant between the radius of a circle and the circumference of a circle. And that relationship is also the angle, the total angle around a circle. So this makes a lot of sense. If you want to do some conversions, some exact conversions, 30 degrees is equal to pi 6, 60 degrees pi thirds, 90 pi halves, 120 to 2 pi thirds, and so on and so forth. And you can make those conversions fairly quickly if you have that table. If you don't, there's a formula for that. It happens to be how many angle in radians per degree. It's 2 pi radians per 360 degrees, right? So that's your conversion factor if you want to convert from degrees to radians or radians to degrees. You can do pi over 180 or 180 over pi because that's the same as 2 pi over 360, right? It's just a simplified version of 2 pi over 360. And here they show that conversion. It's about 57.3 degrees per radian, right? Because there's not an even number of radians per revolution, right? 2 pi of them is 6.28 radians per revolution. So it's going to give you a funky conversion. But it turns out to be much easier to use radians when you're doing mathematics than it is to do degrees. So we use radians. Now, we've got angle. We've got a new coordinate now. Instead of delta x like we were using in chapter 1 and delta x in chapter 2 and delta x, delta y like we were using in chapter 3, chapter 4, we now have a new coordinate to deal with, a new dimension, which is angle. We're going to use delta theta instead of delta x, which is just angle. It doesn't tell you how far something is away, but it does tell you a position angularly relative to where you're at. So if you say, for example, I'm sitting in this classroom and I'm about midway through the classroom here, and I could say, well, the back door of this classroom, since it is over in that back corner to my right, is about 20 degrees from this way, which is, what is this way, east? From east to south. It's about 20 degrees that way. It doesn't tell me how far away the door is, but it does tell me which direction it is, right? So that it's only one part of our system. It's not going to tell us everything. It's just like X doesn't tell you everything about where that door is. Because if the X dimension was here against this wall that I'm on, then the door would be 5 meters in the X direction. But that only tells me how far it is that way. It doesn't tell me how far it is that way, right? So you need to have two numbers. And the other number that we're going to use is going to be, we're going to learn about in a minute. So that's theta. We start with theta, which is our angle. And we're going to do some stuff in rotational motion now concerning theta. And the first thing we're going to do is we're going to figure out in this first dimension, or this first, this is one-dimensional motion now, but it's rotational motion in theta. We're going to figure out what happens when theta changes, and that's what we're going to call angular velocity. So angular velocity is going to be defined the same way that linear velocity is. You take your dimensional variable, which is our delta theta, and we divide by delta time. So delta theta over delta time, how much angle you move through and how much time, is going to be called angular velocity. Instead of using v, we're going to use omega, which is this funny looking roundish w. It's omega. And it's delta theta over delta t, simple enough. Just like this, the velocity was delta x over delta t. However, we are going to define a speed that is going to be different than our speed in 1 and 2 dimensions. And we are going to still use v for this. They unfortunately do use v for this speed. They don't put a vector sign over it or make it boldface or anything. But this is going to be the speed along the edge of the circle that we're moving on. So we have the angle that we move at, and we have the edge of the circle. Now that edge of the circle is going to be a radius of r distance away. So that's our second dimension, is the radius r, and it's going to be defined as the arc length that we pass along, delta s over delta t. Now, earlier we learned that delta s is equal to r delta theta, the radius times the change in angle. That's that 2 pi r thing, right, for the circumference of a circle. But for any angle that is less than 2 pi, we can just plug it in as delta theta here in r, and we can actually calculate the distance we've traveled along the edge of the circle. And if we've traveled that distance in a certain amount of time, we can actually calculate the speed along the edge of the circle. So that's what this v is here in this chapter. I know it's confusing once again that we used v earlier as delta x over delta t, but this one is going to be delta s over delta t, which will be the speed along the edge of the circle. And notice that once you put it into the equation with r delta theta over delta t, you have delta theta over delta t together, which is actually omega. So the speed along the edge of the circle is actually equal to the radius times the angular velocity. So r times omega will give you the speed along the edge of the circle. Now, omega is different than v. Omega is radians per second. It's a rotational speed. It just tells you how fast something is rotating. Whereas v is delta s over delta t, which actually is a speed. It's not a velocity, it's a speed. Okay? Angular velocity is a true velocity. It actually does have a direction associated with it. We're not going to talk about the direction of it yet, but we will later. But this speed along the edge of the circle, the arc speed you could call it, is actually in meters per second. This one's radians per second. This one's actually in meters per second. It's not a velocity because it's not a straight line speed. It's always changing its direction, in other words. And it has two different ways that you can look at it. You can look at it as the change in your distance along the edge of that circle divided by time, or you can multiply the radius of the circle times the angular velocity and get that same thing. Now here's a classic example, a car tire, right? We have our car rolling along the edge of the road, rolling along the road, and we want to know something about the movement of this car tire. The car tire has an angular velocity omega as it rolls along, and since the car tire is always in contact with the road, unless it's skidding or slipping, if it's like peeling out or something like that, then the car tire is moving slower or faster than the road. But as long as it's just rolling on the road normally, it's the speed along the edge of the tire, the speed of movement along the edge of the tire is the same as its speed going down the road. In other words, the road is moving relative to the wheel, is the same speed as the wheel is moving relative to the road. That's a good thing. That's what keeps the wheel from skidding and spinning out. So this v here, which is the speed along the edge of the tire, if you imagine yourself an ant on the edge of this tire and you're moving around as the tire spins, that's your v, and it's equal to the radius of the tire here times the omega, which is the angular velocity, the amount of spinning this tire is experiencing. That gives you the speed of the tire as it rolls along. That will also give you the speed of the car forward, because those two things are exactly the same as long as the tire is not slipping. And here they want us to calculate the angular velocity of a car tire when the car is traveling at 15 meters per second. So that 15 meters per second of the car moving forward is the same as the 15 meters per second of the tire rolling along the edge. The tire's edge rolling along the ground. So this 15 meters per second can go right into that equation, v equals r times omega. And here they explain that in this strategy. So they give us the radius of 0.3 meters. Oftentimes in these problems, they will not give you the radius. They will often give you the diameter. And if they do that, make sure that you divide by 2 so that you have the radius. So it's the radius that's 0.3 meters, and knowing the velocity and the radius, we can use that equation right here and solve it for omega to calculate omega, and that's exactly what they do. They calculate omega, they solve it for omega, and then they plug in the numbers and calculate omega, 50 radians per second for that car going 15 meters per second. Which makes pretty good sense for a car Cars, 15 meters per second is about 30 miles an hour, I think. So that's, that's a kind of a normal speed for a car. We can accept that. So let's move it along. And at and then 50 radians per second. How many times would the tire rotate? Remember, it's about 6.28 radians per revolution. So this would be about 10 revolutions per second. And that's easy to imagine, a tire moving 10 times around every second. They move pretty quickly. It does depend on the radius. The bigger the tire radius, the fewer times they move per second for a given speed, but that's not outrageous. Now, what is it that makes something turn? Why do things go around in circles? Well, it is an acceleration because it is a changing velocity. And this diagram shows that quite well, I think. You have here they don't really show it as an object. They should draw a little point here. And they actually have a pretty good I wonder if this is the one.
Mr. Daly,
Yes.
can you share your screen with me, please?
Oh, did I forget to do that? I apologize.
It's okay.
Let's see, I have to fix something here. Share screen. Yeah, don't be afraid to speak up earlier. I know what
Well, it's okay. I mean, just sometimes it's hard to follow, but I didn't want to interrupt. I wasn't in that.
Definitely interrupt. It's much worth it. We don't want you to go without. Are you seeing it now?
Yeah,
Okay.
I was following along for the most part.
Okay. Already did that. Let's see if this ladybug thing's going to come up for me. Come on. Give me a break. There we go. There we go. So there is a very good let's see, is this the one I like? There we go. So here is our ladybug going around and around and around. And this is the velocity of this ladybug changing its direction every moment of its motion. It's always changing its direction, right? And however, the direction that it's changing is not necessarily obvious. If we go back to our book really quick, we can see the direction that it changes. Here's the velocity vector at one point. Here it is at another point. Velocity 1, velocity 2. How do you take a difference to find the change? Well, the difference, delta V, is the change in velocity or the acceleration. And to take that difference, you put them tail to tail. Remember when you put vectors head to tail, it was adding, but when you put them tail to tail, that's actually subtracting. And you go from V1 to V2, and it shows that the change in velocity vector, which is going to be in the same direction as the acceleration, points towards the center of the circle. So if we take a change in velocity between these two vectors and put this vector right in between them, it will point directly towards the center. So that shows that when you're going around a circle at a constant speed, but you're always changing directions because you're going around the circle, the acceleration is towards the center of the circle. And centripetal means center pointing, so that's why we use that word, and that is the centripetal acceleration. Now, how do we calculate the actual centripetal acceleration? Well, it is technically calculated in 2 dimensions, but because we have this ability to change to a new coordinate system with our delta theta and from our original coordinate system, we can do it that way. So right here we have delta V is, what we're going to do here is we're going to take our delta V and we're going to divide it by our speed, and that turns out to be, let's see if they're showing it here. They're not really showing it here, but it turns out to be delta S over R. It's the same It's the same concept. It's like taking taking the difference divided by the, well, that's not a good way to say it either. But anyway, it's similar triangles is what they're saying here. So you have the up here you have your delta V as this one side of the triangle, and your two V's over here are the other two sides. And you have the same thing with this lower triangle, so that you can get the delta S over R. And they do use a small angle formula in there that we're not going to talk about, but it's just a simple mathematical thing. But anyway, the point being is that when they end up solving it, they get delta V equals V over R times delta S. And the delta, when we divide both of these by delta T, we get V over R times delta S over delta T. Delta S over delta T has already been shown to be our speed along the edge of the circle, which was that omega times R, right? And we have a V over R in here already, which is, again, the speed along, this is actually the delta S over delta T is the V, and this one is the V over R here, which was the omega. If you yeah, anyway. So the point being is that once you get that all put together, you end up with V squared over R instead of just V over R, because this one ends up being a V. This has already got a V in it from the algebra being done here. So we have a very simple equation in the end, just from some simple algebra and a couple of, this one is a geometric trick with the similar triangles, and then down here there's just a little trigonometric trick that they throw in there. They actually don't throw it in, but it should be in there. But this is the only thing you really need to remember, is that if you want to calculate the centripetal acceleration, and all you know is the speed along the edge of the circle and the radius of the circle, it's very easy. You square the speed along the edge of the circle and divide by R, and you will get a value for the centripetal acceleration. You know which way the centripetal acceleration points. It always points towards the center of the circle from wherever you are on the circle. But for the magnitude of it, you just take the speed squared divided by R, and you're done. It's really simple. Easy to remember as well. There's also another form of it, because V equals R times omega. You can actually substitute R times omega into this equation. You get R squared omega squared over R, and then you can just have R times omega squared. So the radius of the circle times the angular velocity squared. And then you can calculate the centripetal acceleration two different ways here, which is nice. Now, that's a lot of stuff. Let's actually use it so we can try to see how it all comes together. We have, let's see, a curve of radius 500 meters. And we're going at a speed of 25 meters per second. So this is like a curve on a highway, a curve out there on I-80. We're going about 90 kilometers per hour, which is about 50, 60 kilometers per hour, 60 miles per hour or so. And a 500 meter curvature, a 500 meter curve is a very gentle turn. 500 meters is, a quarter of a mile almost. And well, it's a little bit more than a quarter of a mile. And so it's a gentle turn at a fairly low highway speed. And we want to know, what is the centripetal acceleration? In other words, what is it that's making us, how much acceleration do we experience to make this turn? Well, we plug in our numbers. 25 meters per second is our speed around that turn, so we square it, divide it by the 500 meters, and we get 1.25 meters per second squared of acceleration. Now, how does that compare to gravity? What is the gravity that we feel in North Platte or Nebraska in general? 9.8 meters per second squared, right? So we're feeling about 1.25 meters per second squared of acceleration around a gentle curve on the freeway. Does that make sense? Can you feel a turn? If your eyes are closed on a highway turn, can you feel the car turning? Yeah. And it's not drastic. It doesn't throw you against the door or anything. And it doesn't make you feel like you're going to come out of the car or something. But you do feel it. You can feel it a little bit. And so it makes sense that it would be a fraction of our weight, which is the acceleration that we're feeling all the time, that we're used to. It would make sense that we would feel it, but not feel it a lot. So that 1.25 meters per second squared is reasonable. Now, let's review again what it is. Let's talk about again why it is that we actually feel this acceleration. So here we are in the car going around this curve, and if let's say that we're going around this curve and we're in a convertible, right? And somebody is holding up a basketball as you go around this curve at 100 miles an hour or something like this. And at this point right here, where this car is at, they let go of the basketball. Okay? If they let go of the basketball right there, what direction is the basketball going to go as the car continues around the curve? Which way? Okay, what do you mean sideways? So on this picture, we've got the direction of the car at this point, which is the green arrow up to the right. We've got sideways, which would be towards the center of the circle. We've got sideways, which would be out away from the center of the circle. We've got...
it also goes backwards.
We also have backwards, right? So, and let's assume that there's no air here. We're driving a convertible on Earth with no atmosphere. So there's no air pushing on the ball. All there is the ball going around the circle, and then all of a sudden you let go of the basketball, and you keep going in the car or on the curve, but where does the basketball go? Keeps going forward in what direction? Which direction of which arrow in this picture? The green arrow? Okay, so we have somebody that says it's going to go in the direction of the green arrow. You guys agree or disagree with that?
With no air resistance, that's correct.
With no air resistance, if you let go of the ball right at this point and the car keeps going around the curve, he says the basketball will go this way in the direction of the arrow. Does anybody agree or disagree? We have one agreement with that. Cassidy, do you have an opinion on that? You want to defer?
I'm not sure.
Not sure?
Isn't it that like if you're on a bus and it stops and you just keep going
Yeah,
forward?
it's the idea. Remember that what does Newton's law say? Newton's first law. Okay, objects that are doing something will continue to do that something unless acted upon by an external force. While you're holding the ball, you're forcing the ball to go in that circle. It is being acted on by the centripetal force. Okay? Because you're holding the ball, the car is holding you, the wheels are holding the car in that circle. If the wheels all of a sudden became non-existent and the car was floating on a thing of air, the car wouldn't be able to turn anymore. It's like having rudders. How many of you have been jet skiing before? Yeah? What happens on a jet ski if you turn off the engine and try to turn? Nothing, right? You go flying off the end of it. You go flying off it, right? Or it goes sliding sideways. Because most jet skis don't have a rudder. They actually depend on the motion of the exhaust, the water exhaust, to turn it. If you buy a really fancy Sea-Doo that has or I think, can't remember, there are a couple of them that actually have rudders on them. You can turn them with power or not, but most of them don't have a rudder on them. So it's the same thing. The rudder provides you with some resistance so that you can turn it. But without that, you can't turn one without its power on. A car would be that way if its tires weren't touching the road. If its tires weren't touching the road, it would just go flying off in whatever direction it was going when it lost its tires, right? So in this particular case, if you let go of the ball right here while it's going in this direction, the ball will continue to go in this direction. So the ball will fly off in the direction of the green arrow, the car will turn around the corner and leave it behind, right? Because the ball was going in that direction at that point. What if we let go of the ball at this point of the turn, down here? Instead of going upward to the right, it's going to go upward to the left, right? Because that's the direction, at this point, the direction of the car's motion is upward to the left over here. If you're right here at this point, then it's straight up, right? And so on. So the velocity of the car is always tangent to the circle that it's turning on, or tangent to the curve it's turning on, and pointing that straight away from the curve at that tangent angle, that 90-degree angle. So the thing that actually turns it back are the wheels. The wheels are always pushing the car back towards the center of the circle. As the car tries to roll straight forward, you turn the wheels towards the center of the circle, and it pushes them back, pushes the car back towards the center of the circle. And your hands pull that ball back towards the center of the circle. And that's your centripetal force or your centripetal acceleration. So here we're going to calculate now the centripetal acceleration of a point 7.5 centimeters from the axis of an ultracentrifuge spinning at 7.5 times 10 to the fourth revolutions per minute. Now notice they didn't tell us the angular velocity here in normal units. Remember our angular velocity before was delta theta over delta t. Delta theta is measured in radians, and time is seconds. Here they've not given it to us in radians per second, they've given us in revolutions per minute. So we're going to have to do some conversion. Here's the equation we want to use for centripetal acceleration in this case, because we have something that's in an angular velocity, so we want to use r omega squared. But our omega is 7.5 times 10 to the 4 revolutions per minute instead of radians per second. So the conversion, first we're gonna calculate radians from revolutions. So it's 2 pi radians per revolution. We have revolutions per minute. There's our conversion factor. And then it's 1 minute for every 60 seconds. That will get rid of our minutes and replace it with seconds. We do that and we get 7,854 radians per second. So quite a few radians per second there. Then we can calculate the centripetal acceleration using that omega. That's our omega in radians per second. We use that with our radius. Our radius was 7.5 centimeters. Convert that into meters, 0.075 meters, and plug it into the equation. And you get 4.63 times 10 to the 6 meters per second squared of acceleration. 4 million meters per second squared. No wonder they call it an ultracentrifuge, right? How much bigger than gravity is that? Take that acceleration divided by g, which is 9.8. You get 4.72 times 10 to the 5th. 100,000 times bigger than gravity. 400,000 times bigger than gravity. It's huge. You ever seen the centrifuge that they put the astronauts in? You ever seen that? It's pretty impressive. Let's look at it. It's fun.
Oh, yeah.
Here's a great picture of a guy in an astronaut centrifuge. Oh, anyway.
I want to try one. It was so bad.
My brother's been in one. My brother, they have one you can go in for fun. They have them all over the place actually, and I think he went to the one at the Ames Research Center in California has one. They're pretty intense. Hard soda.
I'm about to take a test flight in a centrifuge that will produce the pressures on the human body experienced during spaceflight. Okay, here we go. We're practicing up our powers and drops. Some of you are hearing some noise, some vibration, like you're going to go down those stations. Some levels. The simulator recreates exactly the G-forces that passengers will feel on future flights from Virgin Galactic's Spaceship Two. Ready? And ready. Set. One set. One set. Here we go.
It's from mainland 2 in 5, 4, 3, 2, 1. Fire sequence starts in 3, 2, 1.
The pressure on my body is like nothing I've ever experienced before. Beginning to feel the onset of G
So it's 6 times G right here. So anyway, they did a lot of those kinds of tests. They've done a lot of those kinds of tests over the years for astronauts and also for spacecraft because they have to know if the spacecraft can handle those kinds of pressures. I think it was 12 Gs where the re-entry module from the lunar space missions would burn up if it was coming into the Earth's atmosphere. If they went over 12 Gs, it would burn up. So they had to adjust their re-entry angles to make sure that they weren't coming in too fast. Of course, if they come in not fast enough, they'll actually just bounce off the atmosphere and go off into space. So they had to keep it between not too much and not too little.
Bounce off, yeah.
Yeah, yeah. Too bad. See you later. No recovering. They never did it. They never lost anybody in space. They've lost people in the atmosphere, but they've never lost anybody in space yet. So ultracentrifuge, that's fun. Let's go to the next one here. So if you have an acceleration that is centripetal, then of course there has to be a force that is causing that acceleration. And it's really just Newton's second law here that's going to help us to calculate that. If you can figure out the centripetal acceleration of an object, then you just multiply by the force of that object, or by the mass of that object, and you'll get the centripetal force that is causing that acceleration. Force equals mass times acceleration. In this case, centripetal force equals mass times centripetal acceleration. Newton's law is still in effect. You can replace centripetal acceleration with v squared over r, or you can replace it with r omega squared to make that formula a little more useful, but it's still the same formula. One of the useful things also, though, is you can use the same formula and rearrange it so that you can calculate the radius of a particular turn, or the radius of a particular orbit, you can think of it as, using the mass and the squared velocity divided by the centripetal force. So here we're going to combine a few things that we know into a single problem. We're going to calculate the centripetal force exerted on a 900 kilogram car turning around a 500 meter radius curve at 25 meters per second. So that's easy. They've given us the mass of the car, they've given us the radius of the curve, they've given us the speed around the edge of the curve. We just plug it into the formula to calculate the centripetal force. 900 kilograms, 25 meters per second, you square that, divided by the 500 meter radius, you get 1125 newtons. That's your centripetal force. However, in part B, they want to know what is the minimum static coefficient of friction between the tires and the road. Why would you say static coefficient of friction if the tires are actually moving along the road? That's an interesting question, but it's one we can answer. So let's take a look at our whiteboard here. So let's draw it. Here is our car. We're just going to draw the road. We're going to draw our tire. But we're going to draw it from two different angles. There's our tire from the front angle. Here's the treads. Right? The 500 meters is this direction. Getting a little bit faster drawing on this thing. But if we look at this from the side so that it kind of looks like this over here, we have our wheel like that. Wow, that's ugly. And the speed of the car is in this direction, or the rolling motion is this direction. Remember that the tire is rolling this way, and the car is moving this way at the same speed that the tire is moving. So if we zoom in just at this part right here, and we just look at this part of the picture where the tire meets the road, what you see is this. You see a tire, and you see a road, and right at this point, is there any movement? It turns
Oh.
out, yeah, it turns out that relative to tire relative to road, there is no movement. Friction happens when two things slide past each other, but since this tire is rolling along the road and not skidding down the road, not sliding down the road, there is no movement between tire and road here. The road is moving one way relative to the tire moving the other way, but relative to each other, one to the other, they're actually perfectly still relative to each other because they're both moving together. You can think of it. You can think of it that way. Since the car is moving forward and the tire is rolling with it, there is no movement between tire and road here. So it is absolutely static coefficient of friction. The other thing that makes it static is the direction of the force. The car is moving this way, which in this picture would be rolling right at us, right? So in this picture, it's rolling right at us. But the direction of the force is actually 90 degrees to that, isn't it? This is the acceleration. The acceleration is towards the center of the movement as it turns, and that means that's also the direction of the force. So the force is actually 90 degrees to the actual movement of the car anyway. So not only is the tire not moving relative to the road at all because it's not slipping, sliding, or skidding, but also the force that it's applying is actually perpendicular to the movement of the tire. Now this is actually why when you turn a corner at high speeds, your wheel does not spin out, it actually slides sideways, right? Because the frictional force is not enough to hold the tire in place. But that frictional force is a static frictional force until the tire skids. Once the tire skids, then it becomes kinetic frictional force, and that's a whole different thing. So our centripetal force here is actually a static frictional force, and of course, static frictional force we have another equation for. It's not just mass times acceleration, but it's mu static times normal force, right? So we go back to our problem. And we have our, this is the force that we calculated was required to turn the car around that corner. So that's how much frictional force we need. That static frictional force has to equal 1125, at least 1125 newtons. If it's less than that, the car is going to slide. So we need at least this much friction, hopefully more, to be a little safe. We like to have more so that you can go a little faster or do a tighter turn or have a little bit more load in your car than you would normally. So we over-engineer that. But we want that centripetal force we just calculated to equal the frictional force, which is equal to mu naught, or mu sub s times n. And of course, the n for this is going to equal the mass times the gravity of the car. So we go ahead and have this equation now where we solve this in terms of the centripetal force on one side and the frictional force on the other having to be equal to each other. And then we solve for mu sub s. When we solve for mu sub s, it turns out we get v squared over rg. Notice that the mass goes away. It turns out the mass doesn't matter one way or the other. And the reason for that is because if you increase the mass, you do increase the likelihood of it sliding away from its tires, but you also increase the friction on the tires at the same time with the same amount. So if you add more mass, it cancels out, essentially. So the mass doesn't matter. All that matters is the speed going around the turn and the radius of the turn. Of course, gravity is the same all the time, so it doesn't change anything. But the speed going around the turn and the radius of the turn is all that matters for this. And so you can calculate the static coefficient of friction that you need to get around this turn by plugging in your speed around the turn, square it, plugging in the radius of the turn, and of course the gravitational constant, you get 0.13 for your static coefficient of friction going around that curve. Now, why would you use this? Well, car designers and tire designers use this to figure out how big the tire needs to be, what kind of rubber it needs to be made of, and those kinds of things. And sometimes even how many tires it needs. You know, some things need more tires to go around turns than others. So a motorcycle, for example, only needs 2 tires to go around a turn because it's such a lightweight thing, and just doesn't have to deal with the problems that cars have to deal with. So anyway. Here they show a picture of this a little bit better. You have your the weight of the car going down, the normal force going up. The normal force, of course, acts on all four tires. And then the frictional force, which is what turns the car. And this is actually the reason that your turning wheels are the wheels that wear out on a car most often. When your front wheels, which are most cars turn with their front wheels, the turning wheels wear out because they're the things that turn the car. They take most of that friction, and so they heat up the most, and so their rubber evaporates more quickly, and you wear out those front tires very well. Now we're going to talk about banking a turn. We did talk about this a little bit in the last chapter, but now we're going to talk about it in terms of the centripetal force, which we did not, we cut out the last part of that one question in that previous chapter about the centripetal force, but now we can include it, where the centripetal force is going to be part of calculating that banked turn. So here's the picture. We have our normal force, which is perpendicular to the slope of the turn. Our weight, which goes straight down to the earth. And then we calculate the normal force by n cosine theta, where theta is the angle with the flat of the surface of the earth and the bank of the turn. And that will be the n cosine theta will be the perpendicular component of our normal force, which will be equal to the weight. And then we can use this equation to actually calculate the normal force on the car. And that normal force on the car has another component, which is this horizontal component, which is going to be the turning force, or the centripetal force on the car. So they go, and once they've got this, they've got the n sine theta equals the centripetal force, and they've got the n cosine theta equals the weight. And then they take actually a ratio between the two, and to calculate that angle. If you take the ratio between these two, then you get this equation here, where the tangent of theta equals v squared over rg. And that will give you the ideal angle for a particular speed. Or you can solve it for the speed and calculate the angle for a particular speed of a banked curve. And the people that use this are the people who design roads with banked curves, so that they can decide, cars are going to be going at a certain speed around this banked curve, what angle does it need to be? Or we have a particular angle on this banked curve, how fast should cars go around it? You can solve it either way. In this case, we have a banked curve that is banked at 65 degrees. And we want to know how fast it should be going, assuming that the road has no friction. So we solve it for v to calculate the speed. We get 45.8 meters per second, which is 165 kilometers per hour, which is like racetrack kind of curves, right? Racetrack kind of speeds, over 100 miles an hour. So, this is an example to take note of, because you will probably see something like that in the homework. I actually haven't populated the homework questions yet, but I will do that this afternoon, right after class.
Has anyone taken their tests yet?
Yes. I believe at least 2 people have taken the test. So yes, that's the answer to that.
How did they feel? I can't hear them very well.
How did they do on the test?
How did they feel about it?
Well, how did they feel about it? Neither of them are here, so I couldn't tell you.
Oh, dang it.
My son thought it was okay, and he took the test, and I don't know how Andrew felt about it, but I didn't talk to him after he took the test. Okay, let's go to the... All right, section 6.4. We have 6 sections in here. Okay. So, Now let's talk about a force which we call a fictitious force. And we'll actually talk about a couple of them. Here, the first one being the Coriolis force. Well, actually, the first one is actually called the centrifugal force. I'm not sure if they're calling it. Yeah, they're calling it in here. How many of you have ever heard of the word centrifugal force? You ever heard that term before? The centrifugal force is what we call a fictitious force in physics. It's a force that we think that we feel because we're in a reference frame that is accelerating. So a car is an accelerating reference frame when it's turning a corner. What do you feel when a car turns left? When you're in the passenger seat, what do you feel?
You're going right.
That's right. You feel like you're being pushed right? And that is what we call the centrifugal force. It's the force that you think you feel because your body wants to keep going straight, but the car turns in front of you and you run into the car, right? But because you're inside the car, you don't really feel like you're going straight. You feel like you're turning and you're pushing on the outside of the door. I mean, you're leaning into the outside of that door somehow, and something is pushing you there, some weird gravitational something or other. But it's not. It's just that you're just trying to go straight, and the car turns in front of you, so you run into the door. It just doesn't feel that way, right? It's very gradual, and you're turning with the car, so you don't realize it. If you were on a, let's say you've just gone swimming and you get into your friend's car that's a Jeep that has no doors, and your swimsuit's all wet and the seat's really slippery, and you don't wear your seatbelt and he turns a corner really quick, you'll really feel that you went straight because you'll slide right out the car and go straight while the car turns left, right? Because there was nothing to stop you from doing that and nothing to make you feel like you're feeling this centrifugal force. The door wouldn't be there to push you back into that circular motion. But it's not really a force. It's really just you trying to keep going forward. Well, it is a force, but it's not the force that you think it is. It's not a force pushing you outward towards the door. It's the door turning in front of you and you running into it. And then the door pushes you inward towards the center of the circle, right? That's what's really happening. So we do recognize this centrifugal force as a force because sometimes we don't know that we're in an accelerating reference frame. In fact, it's better to say that everybody's in an accelerating reference frame. Nothing is perfectly non-inertial. Everything is always accelerating and moving in the universe, so we're all on these kinds of reference frames. So we have to take into account these forces. There's another one that is called the Coriolis force. And the Coriolis force is kind of an interesting one. Let's see if you can do this thought experiment. Actually, let's see if we can find a video about this. I wish I could make one of these. I've never figured out a way to make a rotating room but I'd love to. What's going on here? This is dumb. This is obviously some movie. I thought it was something else. Okay, so anyway, what we're looking for is a room that's rotating. Let's see here. Yeah. They do this a lot. They do this a lot in movies, but I wish I had one here that showed just some experiments going on in a rotating room. Throwing balls. Let's see if we can find somebody throwing balls in a rotating room. This is a simulation. I want to see an actual. Here we go. Here's one. So this is MIT. They're doing this on a rotating table. It's not nearly as cool. Ours at BYU was way better because it was an actual room that you went into. It was like one of those rooms at the fair where you get in and you stand on the wall and it spins around and around and around and you stay on the wall. I don't know if you've ever seen that. But
I love those.
yeah, those are cool. But ours was even better than that, if you can imagine, because ours didn't go super fast. It actually went pretty slow, and you got into the room and you sat down at a table around a table on this big round bench, and then they closed the doors and they started the room rotating, and then you could start tossing balls to each other. And I always wanted to bring squirt guns in there, and you'll see why in a second. But there's some really cool stuff that goes on. So let's see this video here. So here they are. They're just tossing this basketball back and forth. Very simple stuff. I don't know if I have any sound here or not. I guess not. So this is MIT. Now they're going to do it. Dang it, we lost the ball. What happens to the ball? So
It keeps going straight.
it keeps going straight, but they rotate relative to the ball, right? So because they rotate, the ball looks like it curves from this point of view. It looks like it curves relative to the platform, but you can see that it goes straight across the screen. But relative to the platform, it certainly does curve, right? If you're inside the rotating room, the effect is really freaky because the ball actually looks like it's turning in midair. And you can't tell that it's going straight. You can't even tell that you're spinning. The great thing is when you come out of this room, almost 1 out of 2 people, every other person ends up falling on the ground and throwing up. It's totally awesome. They call it the vomit vortex. Now you're seeing it relative to them. Now you're seeing it relative to the platform. You can see that it does curve relative to the platform. The camera is now rotating with the platform. One of these days I'm going to figure out a way to build one of these on this campus and show this effect in live, because it's just so much fun. And it's just great to see people just falling over when they get out. But can you see now why having squirt guns in here would be super cool? Oh, here he's got his Wilson volleyball. So these guys are from the best. This is the best physics and engineering school in the world right here. And this is what they do for a living, is play on things like this. This is why I wanted to be a physics teacher, because you get to play for a living. It's so much fun. Someday I'll build one. Maybe I should just start with one of these little ones. Actually, the school that I went to also had miniature ones that were old dental chairs that had been modified so that you could spin around in them. And you'd spin around in this dental chair with this table in front of you, and you'd roll things on it. But those ones were so sickening because the room was just going around and around. You need something enclosed, you know. You need something that's truly enclosed. I need to find some old dental chairs. So anyway, that is the Coriolis effect. Now, the Coriolis effect also exists on very large scales. Let me show you what I mean by that.
That's what I've read before. I remember in one of the science classes we were talking about.
So this is the Coriolis effect right here. The Earth is rotating underneath its atmosphere. And as the wind blows along across the Earth, it gets turned by the rotation of the Earth. And that rotation causes, in the southern hemisphere, it causes these tropical storms that they call, this is a hurricane if it's in the northern hemisphere. In the southern hemisphere, they call them willy willies or something, I don't remember what. But that's down in Australia, they call them willy willies. So you get some extreme, I mean, even just in clouds you can see it. This is just a Coriolis force effect, Coriolis effect in clouds. But you get these humongous hurricanes going on. The Coriolis force is not what causes tornadoes. So that's not the thing going on there. I'm looking for a map. Hurricane. So here we go. They call them typhoons in the southeast Pacific, hurricanes here on the east coast and the west coast of southern United States, cyclones down here, and then on this side of Australia, on the bottom side, they call them willy willies. I just think that's hilarious. They don't show it there, but they do call them willy willies. Anyway, so Coriolis force. Some people say that also it causes the water in toilet bowls to rotate, but it's not true. However, the direction that they rotate, clockwise or counterclockwise, does depend on northern or southern hemisphere. And that's because the Coriolis force is from rotation. The Earth is rotating more towards the equator than it is towards the poles. So it's rotating more quickly, and it causes that twisting force up in there. So that's a Coriolis force thing. Here they show that again. So in the northern hemisphere, it's counterclockwise. Southern hemisphere, it's clockwise.
Same for tornadoes, like
No, tornadoes are not determined by Coriolis force. Tornadoes, well, that's a bad way to. I guess it's not true that they're not caused by the Coriolis force, but they're not caused by a Coriolis force from the Earth's rotation. They're caused by a Coriolis force between relative motion of colliding storm fronts. So you have a cold front and a warm front that collide. I think that's how tornadoes are formed. But as they collide, one of them goes one way, one of them goes the other way, and that's what determines the rotation. It's not because of the Earth's rotation. So it can be either way for tornado, if I'm remembering correctly. I think I am. But it may be pretty much always the same way in Nebraska because all of our cold fronts come from the north and all of our hot fronts come from the south. But that's not always true in other places. Some places have their cold fronts come from different directions than ours.
So what's the difference between the centrifugal force and the Coriolis?
So the centrifugal force is this force that makes you feel like you're being pushed outward away from the center of rotation, right?
Okay.
So that's the one that makes you feel like you're getting pushed into the door in your car, or you're getting pulled off the merry-go-round. The Coriolis force is the force that you see something is the force that makes something take a curved path relative to the rotation. So if you're on your merry-go-round and you throw a ball out toward the edge, it'll look like the ball is curving. And so you assume that it's a force that's making the ball curve. But really it's just the merry-go-round that's curving underneath the ball. That's what we saw in the video.
Mm-hmm.
It's also the force which causes the hurricanes to rotate. Because really what you could say that hurricanes are kind of just storms going in straight lines, but the Earth is rotating underneath them. But that's not the only thing that's happening. But the Coriolis force is one of the major factors in causing that rotation. So the Coriolis force is a curved motion, kind of a force that causes a curved motion, and the centrifugal force is this radial motion outward away from the center of rotation. Does that make sense?
Yes.
Now we're not going to talk about calculations with those, we just wanted to clear them up. They are very different from the centripetal force. The centripetal force is a real force. It's not something that you only observe because you're rotating. It's the real force that causes things to turn. These other ones are imagined forces that seem like they're causing something to turn, but they're actually not. It's actually another force that's involved, the centripetal force in particular. We're just seeing it from a different point of view. And so that section is not about, we're not going to be calculating anything from it. It's just to clarify the differences between the perceived forces and the real force that's involved. Okay, so we've talked about Newton a lot. Let's talk about what he really discovered, and that is what is it that is causing gravity? What's going on with gravity? It's not just things that fall to the earth. It's things that have mass attract each other. Okay? With the earth, you have the earth, which is this humongous mass, and it's attracting everything near it. And so that's why things fall to the earth if they're near the earth. But if they're far away from the earth, things won't fall to the earth. But they are attracted by the earth's gravitational force, just like the earth is attracted by the sun's gravitational force. And he was able to determine a formula that described this attraction. And the formula looks like this. The force of gravity is equal to the mass of the two objects multiplied together, mass 1, mass 2, little mass, big mass, however you want to do it, divided by the distance between them squared, and that's the distance between their centers of mass. So the distance between the centers of two planets or the centers of two stars. You have to go from the center of one to the center of the other, especially when they're big objects. And then you multiply by this universal gravitational constant called big G. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And that will tell you the gravitational pull or the gravitational force between any two objects of mass with a distance r between them. Now, how is little g and big G, how are little g and big G related to each other? Well, little g is the number that you get when you plug the mass of the Earth into this equation and the radius of the Earth into this equation. Then you will get little g times m, which the little mass would be the mass of anything that's on the surface of the Earth. Okay? So they're going to do that down here a little bit. It's right here. Big G times the mass of the Earth divided by the radius of the Earth squared will give you 9.8 meters per second squared. So that's why little g is only for things near the center of the Earth, because that's near the radius of the Earth. If you go very much higher than the Earth's radius, if you go up even to Mount Everest, which is just a little bit longer than the radius of the Earth, it's not much, but even a little bit, and it makes it a bigger number down here, which means the g gets smaller. And so you can lose weight just by going to the top of Mount Everest. Even if you don't lose weight just getting up there, you can lose weight just being there, right? And the higher you go above the surface of the Earth, the less the gravitational pull of the Earth has an effect on you, because this r gets bigger and bigger and bigger, therefore the g gets smaller and smaller and smaller. So, let's calculate the acceleration due to Earth's gravity at the distance of the moon. How much is the moon accelerated by the Earth compared to g on the surface of the Earth? So we have little g, big G over m, big G times big M over r squared, big M being the mass of the Earth, r being the distance from the Earth. Normally that would just be the radius of the Earth when we're on the Earth's surface, but now we're going to take it to be the distance from the Earth to the moon, which is 3.84 times 10 to the 8 meters. Now remember that this is from the center of the Earth to the center of the moon. That's the distance. If you take it from the surface of the Earth to the surface of the moon, it's shorter, and it's significantly shorter. So you need to take it from the center to the center. But then you get 2.7 times 10 to the minus 3 meters per second squared. 2.7 millimeters per second squared. Not meters per second squared, millimeters. So the moon is being pulled significantly less towards the Earth than we are. Gravity is a very small force, but it does reach out there quite a ways. It will reach forever, in fact. But it is quite a small force, even on big objects. Not much acceleration. The Earth, as the moon moves forward, every second that the moon moves forward through space, its movement is perpendicular to its distance from the Earth, it gets accelerated 2.7 millimeters towards the Earth, or it gets moved 2.7 millimeters towards the Earth for every second it moves forward. Anyway, not very much. Doesn't need to be very much. So part B, what do they ask? Calculate the centripetal acceleration needed to keep the moon in its orbit and compare it with the value of acceleration due to Earth's gravity. I just found, okay, so working, let's see here, you can see that. So omega centripetal acceleration, 2.72 times 10 to the minus 3 meters per second, same thing. So G is 2.7, the centripetal acceleration 2.72, pretty much the same number. And comparing that to 9.8, I don't know if they actually calculated it, but it's less than, yeah, they did. It's less than 1% of the acceleration found on the Earth surface. So pretty small. Here's an interesting thing, though. The Earth is holding the moon in its orbit, but the moon is also pulling on the Earth. So as the Earth pulls on the moon with this particular force, the moon pulls back with the same amount of force. It doesn't move the Earth as much because the Earth has so much more mass, but it does move the Earth. And so this is what the Earth's orbit looks like going around the sun. It's not actually an elliptical path. It's actually a wiggly elliptical path. That little wiggle in the Earth's orbit is because the moon is shifting the Earth back and forth across its nominal orbit. If the Earth had no moon, it would be much closer to this elliptical orbit. With other things, it's much more extreme. With things like Pluto, it's much more extreme because Pluto's moon Charon, or Charon, however you want to say it, is almost the same size as Pluto. So it has a much more eccentric orbit. But Earth's moon is quite a bit smaller than it, so it's not quite as eccentric. It doesn't quite bounce around so much. The other thing that that the moon is responsible for as far as gravity is concerned is low tide and high tide, right? As the moon goes around the Earth, it actually pulls the water on the Earth towards it. And you get a particularly high tide if the moon and the sun are on opposite sides of the Earth. You can get particularly high tides. Or if the moon and the sun are on the same sides of the Earth, then you can get a particularly high tide. But if it's just the moon and the sun is just somewhere on the random place, the moon pulls on the tides much more than the sun does. And you can get these high tides, high water mark. Oh, dang it, what just happened? There we go. There we go. So here they show the different tides here. They have the spring tides where the moon and the sun are on the same side of the Earth, or the moon and the sun are on the opposite sides of the Earth. And that's when you get the biggest tidal features on the Earth, where it's really stretching out the water on the two sides of the Earth that the moon and the sun are. And then you have the neap tides, where the moon and the sun are 90 degrees to each other. The sun's not pulling as hard, but it is still pulling, so it kind of lowers the normal tide that you would get from the moon being over here, and you get that neap tide, they call it. And these tides do occur all over the place. Tidal forces happen not only with planets that have liquid water on them, but also with planets that don't have any liquid at all. For example, Mercury has tidal forces on that actually change the shape of Mercury itself. It actually stretches Mercury towards the sun because it's so close to the sun. It actually cracks up the surface and causes volcanoes and other things to erupt. How do we get into things like microgravity and weightlessness? Well, that's interesting. Let's talk about that just for a second. Here are some pictures of people on the International Space Station, but probably the best stuff to see are the So that's just water he's squirting into the atmosphere of the International Space Station. Just out of a water drinking bag there. When water sticks to itself? I don't know, it's just the adhesion forces, it's just the forces of water. The term for adhesion forces of water is it's that force that they use you get the water over the top of the glass. I can't remember what it's called. But it's just liquid adhesion forces. Now the real question is, why doesn't it fall? Why doesn't it fall apart? And it all comes down to the same thing. Gravity, when we're in our normal experience here on Earth, pulls things down towards the ground as far as it can. So when it hits the ground, it spreads it out. And that's why water spreads out on the ground, is because gravity is continuing to try to pull it further and further down. The only reason we don't spread into a puddle on the ground is because we have skin, right? Our skin is an extremely strong organ that keeps our bag of water all in the shape that it's supposed to be in, because we are just a big bag of water. Gravity would otherwise just pull us into a puddle on the ground if we didn't have skin. But in the space station, instead of sitting on the ground and allowing gravity to pull them straight towards the Earth, they are moving perpendicular to the Earth. So this is what's happening. Here's the Earth. Here's the International Space Station. If the International Space Station was just sitting up here, it would fall towards the Earth and crash, and then they would become a puddle, or they would fall in a puddle, one of the two. But they don't do that. What they do is they move this thing forward this way around the Earth, so that as it moves forward, it actually is moving forward more this way, perpendicular to the Earth. As it moves forward, it does fall, but it only falls a little bit for every distance it moves forward. So this is how much it falls. And then it moves forward this way. Dang it. Can't draw very well. Then it's moving forward this way, and then it falls a little bit this way. And then it moves forward this way, and then it falls a little bit towards the Earth this way. And if you keep doing this continuously, you will never hit the Earth. Well, and that's exactly what they do. To get into orbit, they blast off from Earth, and then they turn the spaceship this way, and they blast themselves perpendicular to the Earth's surface. And if they get at just the right speed, then they will fall the right amount so that they stay the same distance from the Earth as they're moving around the Earth. You know, they don't really fire the rockets and then fall, and then fire the rockets and then fall. They fire the rockets, get going a particular speed that they've calculated. They know what speed they need to go, so that their falling makes them fall around the Earth instead of to the Earth. So orbit is nothing more than falling around the Earth. You're just never going to hit the Earth because you're going forward fast enough that it's like falling over the edge every time, and over the edge there's a new edge, right? So they're just falling around the Earth. And that ball of water never flattens out because it's falling at the same speed that it's finding a new edge to follow, right? It's the same thing as jumping off of a diving board for those very few seconds that you're in the air, depending on the height of the diving board. You don't feel your weight at all because there's nothing to push up against you. And if you could jump off a big enough diving board, you could be weightless for a very long time until you hit the bottom. But they're just diving off a diving board where the bottom of the pool keeps moving because they keep moving around it, right? They keep moving off the edge of the Earth until they have a new edge. This was the edge the first time. This is the edge the second time. This was the edge the third time. And they just keep moving around. They keep moving the edge because the Earth is round, and they can keep moving the edge. Yes, sir?
Is that why you get a sense of weightlessness when
That's exactly why you get a sense of weightlessness in an elevator, because you're dropping the edge out from under your feet, right? So there's nothing pushing up against you to make you feel that weight. And so they can do the same thing with an airplane. They'll fly an airplane up above, and then they'll go going a certain speed. They put it in a little loop like this, and along this part of the trajectory, as this airplane goes up in this parabolic loop, it's actually hyperbolic, but as it goes up in this path like this, during this part right here, you have about a 2 or 3 minute time that you feel weightless. So they take you up in an airplane, and they'll actually go up and down, and up and down, and up, so you have weightlessness every couple of minutes. And you can do experiments, and you can have fun with it. And you pay a lot to do it, but I've always wanted to do it. I need to do it someday. But the weightlessness is nothing more than putting yourself in a position where there's nothing that's going to push you back. There's nothing that's going to push up on your feet to make you feel your weight. That doesn't mean gravity's not pulling you anymore. Of course, gravity's pulling on the space station. That's what's keeping it in orbit. But it just never reaches the ground because it's going over the edge of the Earth every second that it gets pulled down towards the Earth. Same thing with the elevator. It just drops out under your feet, and then you feel that weightlessness or less weight for a short period of time. There's some other really great experience. Let's look at this one. There's our washcloth puck.
It's come down to this little tiny hockey puck so that it saves the space. When you open up the hockey puck, and you pull on the washcloth, this is the one we can use for the experiment today. So when you open up your hockey puck and turn it into a washcloth, it's compressed and a great big ice in there. Okay, so here's my washcloth. And magic trick. And now we get this soaking wet, and then we're going to see what will happen when we ring it out. American Canada suggested that I did this in a bag, but bags don't hold water in space, so instead I fill the water bag. This is drinking water. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. The microphone's here on top. And now let's start bringing it up. It's really wet.
It's kind of fun. They do a lot of experiments with water in the space station.
It's so cool how it just stays around the water.
Yep, there's nothing to take it away. They there's a soccer ball orbiting in space, really? They do experiments with putting water on strings and all kinds of things. But anyway, it's a lot of fun. Worth looking at. So, weightlessness. Now let's talk about the Cavendish experiment, which the Cavendish experiment was an experiment that proved Newton's theory to be correct right here on Earth. Of course, Newton used planets. He used the observation of planets and lots of calculations to create his general law of gravitation, or universal law of gravitation, as it is called. But it's very difficult to observe the attraction of small objects towards each other because of their mass due to gravity. When I say small objects, I mean anything smaller than the Earth-like objects, right? And how are you going to have a laboratory with big objects like the Earth? You're not going to. But Cavendish figured out this way to do this, and this was a couple hundred years ago, quite a while ago. Can't remember exactly when it was. Let's see if it says a date here. 1798. So 100 years after Newton and over 200 years ago. So this is what he did. He has these two very large masses that are fixed. So he did this in a room where everything was sealed up. There was no air coming in or out of the room. It was very, very quiet. It was done in a place that was very stable, on a big block of granite or something, and just to prevent any vibrations or anything. And then he has these other two masses that are on a pivot. They could also be hanging or something like that. But connected to these other smaller masses is this mirror, And then there was a light source shining on the mirror, and the mirror focused the light over onto this scale over here. So you have this long arm of rotation. And over time, what he started with these masses further away from each other, and then over time he measured as they would move towards each other. Now, due to some vibration and some air every time you open the door or whatever else you go in the room, there would be variation. But over time, he was able to observe, and he was able to adjust the experiment so he had very little things interfering with the experiment. He was able to observe that these smaller masses would slowly gravitate, literally, towards the bigger masses, and they would rotate in and eventually touch. And they actually have pictures of his experiment. I mean, his original one, I think, is still around, or maybe a copy of it. Can't remember. Cavendish. That's the wrong Cavendish. Here we go. Here's some of his original drawings for his experiment, and then I believe that this is his actual experiment right here. So it's built inside of this room, and you can see the telescope on one side. These two very large masses. I believe they were made of lead balls or something like that. Yeah, 348 pounds. So this is his. This is either a recreation or his actual one. I can't remember. But it's sealed inside of a room, and then he has a telescope so that he can see inside the room. He did that so that he could enclose it completely. And then he had the smaller masses were these ones here that rotated with the mirror. So he was able to prove that Newton was correct and show that masses do attract each other just by being massive, just because they have mass. And he showed that it was actually a 1 over r squared dependence, just like Newton said it was. Okay, the very last thing I'm going to talk about is a guy named Kepler. Kepler was, he was around about the same time as Newton, maybe a little bit earlier, I think, maybe. Can't remember who was first. But anyway, about the same time-ish. And I want to say Kepler was a little bit earlier, and Tycho Brahe was a little earlier still, but they were still within 100 years of each other. And they were studying, Kepler and Brahe were studying celestial objects and making recordings. They were some of the first scientists that really made a lot of measurements of stars, planets, and other heavenly bodies out there, particularly things like comets and things. But one thing that Kepler did is he was able to put together a couple of laws about how planets move. Kind of like how Newton put together laws about how gravity works. And the first law is that the planets move in elliptical orbits. Now remember, this was the time when people were still trying to convince everybody that the Earth was the center of the universe. Right? Not just the solar system, but the center of the universe. And so people were trying to figure out why these stars out there, which they had discovered by that time were actually planets, but why these planets out there had these funky motions, because everything else moved in circles, but these planets moved in these weird shapes across the sky. And the only way to explain that was that the Earth was not the center, that the Earth was actually going around as well. And Kepler was one of these first people, Brahe was also, and Copernicus and others, but Copernicus? No. Anyway, I sometimes forget who was the heliocentric and who was the Earth-centric. But anyway, Kepler and Brahe certainly realized that the Earth was not the center of the universe. And Kepler said, well, it turns out that all the planets are going around the sun. And he didn't say anything about the stars, he just said the planets. We know that there are, at that time, I think they knew that there were 7 planets out there. They didn't know about Neptune or Uranus, one of those two, and they didn't know about Pluto. But they did know about 7 of them, and they knew that he was able to discover or determine that they all moved in elliptical orbits. And what is an ellipse? Well, the definition of an ellipse is a shape that is kind of this, curvature shape that has two focal points, and if you took a string and tied a string that was a particular length that went around both focal points and hit just on the edge of the orbit of one of the planets, and then you stuck a pencil in that string and drew a circle around and kept that string tight, that would be an ellipse. That is technically the definition of an ellipse. If you want the mathematical definition, you have to say that the length of this side of the string and the length of this side of the string, when they're added together, is always the same, but it amounts to the same thing. But the point is that you have these orbits of these planets that always follow this kind of a shape. Now, for almost every planet in our solar system, these two focuses, or the plural focus is foci, these two foci are actually both inside the sun. They're almost right next to each other inside the sun. So most orbits of planets are almost circular, because an ellipse, a circle is actually just an ellipse where both of these focuses or foci are on top of each other, are the same point. And for most planets, they're very close to each other, both within the sun, both within the sun's radius. The Earth has an almost perfectly circular orbit, as do most planets. Some of the planets are not so circular. Pluto in particular is very uncircular. It's very elliptical. The orbits of Halley's Comet and the Hale-Bopp Comet are both very elliptical, extremely elliptical. So elliptical that they only come around close to the sun every couple hundred years. 80 years for Halley's Comet and a couple hundred for Hale-Bopp, I think, or something like that. But anyway, the point is that he discovered this, and he was able to measure it and also make some calculations about it. Another law that he came up with, this is actually related to this this elliptical orbit law and Newton's second law, Newton's gravitational law, which is actually, this is where Newton got some of his information for doing his calculations, and that is that if you allow a line between the sun and a planet to sweep out little triangles, little pie pieces of area in certain times, so like the distance between A and B in time would be 1 day, and C and D would be 1 day, and E and F would be 1 day. All of these areas of these little pie wedges would be the same area. And that's actually a geometrical law as much as it is a planetary law, but he just didn't know it at the time. So he added as much to geometry as he did to astronomy. Kepler's third law is the law that we're going to use for doing some calculations, and that is the relationship between the period, or the year, the time that it takes a planet to go around its orbit once, which is the year of a planet, and the radius of the planet. And so this is the relationship. The period is the capital T. So if you take the period of a planet and square it, it will be proportional to its radius cubed, or the radius of its orbit cubed. And that radius is actually its average radius, because if it's an elliptical orbit, its radius is not always the same. So the radius is its average radius. And you can take the periods of two planets and compare them. So if you take the period of one planet and square it and divide it by the planet of a second planet squared, then it will be equal to, not just proportional to, but it will be equal to the radius of the first planet cubed and divided by the radius of the second planet cubed. So that's the equation we'll use, and we'll use that in this example right here. So we have the moon orbiting the Earth 27.3 in 27.3 days, and so that's its period, right? Its average distance is 3.84 times 10 to the 8 meters from the center of the Earth. And we want to calculate the period of an artificial satellite orbiting at an average altitude of 1,500 kilometers above the Earth's surface. Notice that they say above the Earth's surface. The radius of the orbit is from the center of the Earth to the radius of the orbit. So we have to add the radius of the Earth to that. And they do that. They add the radius of the Earth to it, and they get both radii, and they have the period of one of them. So they solve for the period of the second one right here. Notice that they keep all the cubes and the squareds, all these things, all these numbers, keep them all organized. And then they solve for T2, which is the period of the artificial satellite. Then they plug in their numbers, making their conversions. They're converting from days to hours. They're converting from kilometers to meters. In this case, they actually just keep it in kilometers because they're both in kilometers and it cancels out. But you do want to convert to hours, and you get 1.93 hours for that satellite that's only 1,500 meters or 1,500 kilometers above the surface of the Earth. So, that is that. I think we're done. Here they have a chart of all the different radiuses and periods of the planets going around things, and moons going around planets and everything else. So, but that's all I have for you today. So I will have the homework up and running for you in probably the next 30 minutes or so. And you have the exam, of course, to do this week. It's just going to be the 3 of us, or the 4 of us this week. Also, because we have so many people missing, I think we'll actually take a break on a lab for this week. And we'll do, instead of a lab tomorrow, I will be here if anybody wants to do exam review or homework tomorrow. So, catch up on things. What's that? We were doing labs. We've done labs on Tuesdays so far this summer. So we did lab on Tuesday, and then we did homework review Wednesday. We did lab once on Wednesday, didn't we? Can't remember. But
Tuesday was
we did lab Tuesday last week. We've been trying to do our lecture Monday, take a break from lecture and homework for a day so you can get started on it, and then do homework review Wednesday, and do the lab Tuesday. Is what we've been trying to do. So. But we'll take a break from lab this week just so that we don't have to have too many people making up labs when they come back next week. And then next week we'll do a lab again. Next week we'll be getting into energy and collisions, so we have a lab for that. I'm sorry? I didn't hear what you said. I'm still not hearing what you're saying.
You're right about Copernicus.
Oh, Copernicus.
Yeah.
Oh, yes. Copernicus is there for sure. Copernicus, Galileo, Newton, Kepler. They don't list Brahe. I like that name, Brahe. Tycho Brahe actually discovered that light has momentum. He didn't discover it, he predicted. When he saw, because he was around when, he was alive when the Halley's Comet was going by, and he was watching it as it went around the sun, and the tail was pointing away from the sun. He said, I think it's the intense light from the sun pushing the tail of the comet away from the sun. And he was right. But he had no idea why he was right, but he was right. It turns out that because of some quantum mechanical effects and other things that we discovered in the 20th century, that light does actually have momentum even though it has no mass. So it's kind of interesting that he was able to make that statement. But I mean, he wasn't the first one to make a statement like that. 200 BC or something like this, Democritus said that if you break things down small enough, eventually you won't be able to break them anymore. And he said that thing we'll call the atom. He actually coined the word for the atom and predicted that we'd discover it someday, and we have. It's just not what he thought it was. Again, it's not the same reason that he thought it was, but still, the philosophy of some of these great old scientists is amazing. They were really quite brilliant. So,
Since light momentum would stop,
I'm sorry?
would it just stop when it's light?
Does light stop when it imparts momentum, for example? No, it gets absorbed. So when light imparts its momentum to something, it either reflects off of it or is absorbed by it. If it reflects off of it, it'll change the light, well, it doesn't have to change the light, but it can change the light, can change its frequency. But if it gets absorbed by it, then all kinds of things can happen. So, but it doesn't stop it. Light doesn't stop. It's either absorbed or reflected. So, light doesn't slow down either, unless it goes into another material. Yes?
So the exam, can we take it tomorrow during
Sure. Yeah, you can take the exam tomorrow during class if you don't feel like you want to come in. Yeah, that's fine.
When is that force sensor supposed to get here?
It didn't arrive yet?
No.
Oh, that's no good. I don't know when it's supposed to get there. I sent it that same day. When was that? Wednesday? Tuesday?
Yeah, Wednesday. Or Tuesday, sorry.
It was Tuesday, I think. Yeah, I don't know. I would assume that it should be there already.
No, I got home from work and I didn't see anything on my front porch, so.
It came. I sent it in a padded envelope, not a very big one.
Oh, maybe it's in my mailbox then.
Could be. Do you have the force sensor? You just didn't have a way to connect it. Is that correct?
Yeah, the Go link on that.
That Go link. That should come in a yellow padded envelope. It's not a huge envelope, but it's not really small either. So.
It's probably in my mailbox then.
Okay. Yeah, I hope so.
So after I'm done with the lab next week, the collision one with the cars or whatever, I'll bring the stuff back to the college.
Okay, and I will start putting together a new box for the remaining labs. Now there is one lab that we will do. I think I can send you. Let's see, how many people do we have in this class? Here we have 4 here, and I have 2 sets of that lab. I think that I can send you the kit for this other one. I'm worried about packing it because it's a little bit more delicate. So,
when would we do that lab?
that one comes when we do the torque. So that's like chapter 9 or something. Statics and torque.
Well, if there was anyone that would go to Broken Bow, I could just pick it up from the college too.
Yeah, I'm trying to think of the best way to do. How would you guys feel like? You guys all work, right? You don't work, but you work, and Packer works, and I'm just wondering if maybe we take a field trip to Broken Bow and do it all together as a class.
That would be cool.
I work Monday through Friday, 7:30 to 4:30, so I can take a day off.
Okay. We might. I'll talk to the other 2 students and see if we can arrange to take a field trip up to you, just so we can all work together as a class one day. And if we can work that out with everybody, then we'll come up and take all the equipment up there and do it together as a class. But I'll talk to everybody this week by email and see what we can do for that.
Okay.
All right. Any other questions or comments or concerns?
I have one, sorry.
Okay. Send me an email so I don't forget. But yeah, I'll do that for sure. And what was that, Cassidy?
Okay, so for that part of the lab where it's the cooperating fans,
Yes.
like not the dueling, but the ones that are going together,
Yes.
you're supposed to have like a clamp that holds it down.
That holds what?
Or like, there's a clamp that you're supposed to connect the force sensor to.
Oh yes. So for that part, there's in your kit, I believe I put a little aluminum post that has threads on one end.
Yeah.
That will screw into the top of one of the plastic cars, and then you can connect the force sensor to that. Or are the fans supposed to go on the car? I can't remember. Let me take a look at that really quick. I'm trying to remember how that goes.
Yeah, because the fans are on the car, and it shows
Okay,
that
right.
it's connected to a clamp at the edge of the table.
Okay, and I didn't include any clamp with your kit?
No.
Okay. So what you can do is you can just if you can tape excuse me. You could tape the force sensor to something that's not going to move if you want to. Just use some painter's tape or something. Or let's see, what else can you do with that? Anything that you can connect that aluminum post to, you can connect the force thing to that post, and then that post to connect it to whatever else. So just kind of improvise and see what you can do. Because normally what we do is we have a track that the cars move on, but it was much too long to send the track to you in the mail. So,
Yeah.
and sending the track up there is just a major pain in the neck.
Yeah, and that was kind of hard too, because you're supposed to have that track when you're using the spring scales.
Yeah, it makes
And
it,
so it's hard. It was like impossible to to hold the spring scale where it needed to be without the car moving.
yeah, I understand. It's actually hard as it is on the track as it is anywhere else. That
Yeah.
part is a little bit challenging no matter what, just because every little tiny little force pulls the thing along, you know.
Yeah.
But you know, you just kind of got to work with it and see what you need to do to make it work. But hopefully, it's not too much trouble.
Yeah.
I apologize. I apologize for the difficulty of doing labs remotely. That is a challenge. We're still working on ways to do that. I actually have a new car for doing this, but I just got it and I haven't really learned how to use it. So I didn't send it to you. I didn't want to send it to you having not tested it yet. So it's a car that has all the sensors inside of it. It has the force sensor and the motion sensor and everything built into it. And
That's cool.
yeah, it's really cool. I don't know how to use it yet, and I didn't want to, you know, send it to a student without knowing how to use it myself. So, but anyway, yeah, anything that you have to kind of work around and improvise a little bit to make it work, just go ahead and do what you need to do and make notes on what you did. And if it doesn't work out, don't worry about it. Just move on. The most important thing about the lab is to learn as much as you can, and you can learn as much by trying to make things work as you can by just having them work all the time. So maybe even more. So, and you won't be docked points if you don't get through things because things aren't working exactly right. So don't worry about the completion of things so much as the participation in the lab.
Yeah, it takes a lot of time.
I understand. And don't spend any more than 3 hours working on your lab. And, you know, keep track of your time, because these students here are not going to spend any more time than that on their labs. So don't spend any more time than that. Once you get to about the 3 hour mark, just turn it off, do the homework at the end of the lab, and just write a note and say, you know, I couldn't get through with all of this, but I did complete these things, and you'll get full credit. So.
Well, yeah, I'll go get that, and when I have time, I'll start on it.
Okay. Any other questions at all?
Not that I know of.
All right. Well, if you have any, please email me or call me, and we'll talk.
Oh, I do have a question.
Yes.
Tomorrow for my test, I'm going to the college, like around, like I'll take my test around 3 or so.
Okay.
Do you need to know who you're sending the password to?
You're going to Broken Bow, right?
Yeah, I'm going to the campus.
Okay. I'll just send it to Broken Bow, and they know what to do with it. So
Okay.
nothing to worry about.
All right. Sounds good.
Okay.
Thank
have a
you.
good one. Bye.
Bye.